Hi everyone. In this video, I'm going to go through section 4.1 of your lab handout, which is building the IF filter and then using the network analyzer to measure the frequency response function of the IF filter. Now for this part of the lab, you're going to need a 1.5 kilo ohm resistor for R1, a 100 ohm and a 1 kilo ohm resistor for R2, a 20 kilo ohm and 10 kilo ohm resistor for R3, two 1 nanofarad capacitors, and then an OP97 op-amp. So the very first thing that I'm going to do is I'm going to connect my ground to the circuit. So this entire rail is going to have a ground voltage of 0 volts. Next, I'm going to place my op-amp into the circuit, and now we can connect our resistors and capacitors. So first for I1 equals 1.5 kilo ohms. Now, a 1.5 kilo ohm resistor has the color combination of brown, green, red. So take out a brown, green, red resistor from your kit and then connect it to the breadboard. Next, I'm going to connect R2, which R2 is a parallel combination of two resistors, 100 ohm and 1 kilo ohm, to give an approximate value of 90 ohms. The 1 kilo ohm resistor has color combination of brown, black, red. So take out a brown, black, red resistor from your kit, connect one end of it to R1 and the other end to ground. And then the 100 ohm resistor has a color combination of brown, black, brown. So take out a brown, black, brown resistor from your kit and then connect it in parallel with the 1 kilo ohm resistor. Alright, so we have R1, we have R2. Now I'm going to connect the two 1 nanofarad capacitors. The first 1 nanofarad capacitor connects I1 with the inverting terminal of the op-amp, and then the second 1 nanofarad capacitor will connect to I3. Now for I3, we're going to, instead of using a parallel combination, we're going to have to use a series combinations of two resistors, 20 kilo ohm and 10 kilo ohm. The 10 kilo ohm resistor has a color combination of brown, black, orange. So take out a brown, black, orange resistor from your kit and connect one end of it to the 1 nanofarad capacitor. And then take out the 20 kilo ohm resistor, which has color combination red, black, orange, and then connect that between the 10 kilo ohm resistor and then the inverting terminal of the op-amp. So we have R1, we have R2, we have R3, we have our two capacitors, we have the op-amp, and we have ground. The last step is to connect the non-inverting terminal of this op-amp to ground, which I'm going to do here. And now we can actually set up our positive power supply and negative power supply voltages in order to power this op-amp. Here's the negative power supply, which is solid white and labeled V-. I'm going to connect that to this rail so that this entire rail has a voltage V- of minus 5 volts. And then I'm going to connect the positive power supply to this rail here so that this entire rail has the positive power supply voltage of 5 volts. Now I'm going to connect the op-amp to V+ and V-. And then the last thing that I realized I haven't done yet is I haven't connected the node between this 1 nanofarad capacitor and I3 to the output terminal of the op-amp. Alright, so we have our IF filter circuit built. Now let's connect the waveform generator input W1, which is solid yellow, to the input terminal of our IF filter, which in this case is the positive terminal of the resistor I1. Now we can set up our channel 1 and channel 2 measurements. For this part of the lab, channel 1 is going to be measured as the input voltage. So I've connected the scope channel 1 positive cable labeled 1+, which is solid orange, to the input terminal of our IF filter. And then our scope channel 2 positive cable is going to measure the output voltage at the output of our op-amp. Also, both the scope channel 2 negative and scope channel 1 negative cables are going to be connected directly to ground. So we've finished building the IF filter circuit. Now we can head over to the Waveforms app and actually use the network analyzer to obtain a plot of the magnitude of the frequency response function hj omega of this IF filter. So to do that, double click on the Waveforms app. First, we need to actually set the positive and negative power supplies to plus or minus 5 volts. Here's the positive power supply, and then the negative power supply at minus 5 volts. And now I'm going to click this button here, which should say master enable is on, which means that both the positive and negative power supplies are enabled. Now we can head over to the network analyzer. I'm going to full screen this. Before we can actually obtain a plot of the magnitude of the frequency response function, we need to change a few of the configuration settings on the network analyzer. First of all, our x-axis is going to have a linear scale, not logarithmic. The start frequency is going to be 50 kilohertz, and the stop frequency is going to be 200 kilohertz. We're going to use 500 samples. Since we're not going to be performing a measurement of the phase of the frequency response function, we can deselect the phase checkbox. Our y-axis is going to have units of magnitude of hg omega, which is gain. So change it from dB to gain. Since our IF filter has a theoretical gain of 10, we're going to change the top of the y-axis to something slightly greater. So how about a gain of 12? And if we have a gain of 10 in our IF filter, then an amplitude of 1 volt would get amplified to 10 volts, which is greater than the plus or minus 5 volts limit, and so we would have clipping. So to be safe, change this amplitude here to 0.25 volts or 250 millivolts so that we can be certain that there's no clipping in our output. Now I can press single to perform a single acquisition of our output, and we see extremely clearly that this IF filter has been constructed correctly, and it's operating as a bandpass filter with center frequency very close to 100 kilohertz, and then an approximate gain of 10 at the center of the passband. Now it turns out that it's not a trivial difference, the center frequency of this IF filter compared to the theoretical center frequency of 100 kilohertz, because our IF filter has a 3 dB bandwidth of only 10 kilohertz, which means 5 kilohertz on each side. So actually, a frequency of 100 kilohertz has about 0.707 attenuation relative to the center of the passband. And this will be important since in the last section of the lab, you'll be computing the local oscillator frequencies to correspond to the center of the IF filter, and so the difference between 95 kilohertz and 100 kilohertz is pretty significant. So record the center frequency of this IF filter. In my case, it's around 95 kilohertz. If you want to be certain, you can use this cursor tool and hover over the peak of the IF filter, and you can see that the center frequency is about 94.8. Actually, it could be exactly 95 kilohertz. But so record the center frequency of the IF filter in your lab handout, and this is very important since this is what you're going to use to determine the local oscillator frequencies in section 5 of the lab. Now in the post lab, you're going to be plotting the CSV data corresponding to the measured curve of the magnitude of the frequency response function on the same graph with the theoretical curve that you obtained in the pre-lab. So head over to export and save CSV data of this plot here. Now make sure that all these other options, comments, notes, headers are deselected, and that only labels are selected so that you have a pure CSV file which can be read into MATLAB. Press save to save the CSV data. Also save an image plot by heading over to the image tab and pressing save. Alright, so we've successfully built an IF filter with a center frequency very close to 100 kilohertz and a gain of approximately equal to 10. And in the next video, we're going to build the envelope detector portion of our superheterodyne receiver.